Got it. I will. Little background. I'm Luke Walls. I was a researcher at Oak Ridge National Laboratory for many years, and Kothe is a colleague of mine who came to the lab. Has it been 20 years? I don't know.
Almost 18 years, so not quite
Almost.
20.
Okay, and so I left the ORNL and I went to the University of Memphis and established a program called Endeavor. And this is a part of a series of seminars, technical seminars, that were put together to showcase expertise in various areas. And Dr. Doug Kothe is a premier computer scientist, researcher with a broad background in supercomputing technology and its applications. And it's very distinguished honor to have him as part of this series. And I really appreciate the time you've taken to do that. If you would be so kind as to do a little bit broader introduction of your work experience, I would appreciate it.
Sure, Lou, and thanks. I've been in the DOE lab system for 38 years. And I've spent time at Los Alamos, Lawrence Livermore, and now Oak Ridge. And I'm actually a trained nuclear engineer, but I've spent my entire career developing applications to simulate complex physical phenomena in the engineering, in the energy, manufacturing, and defense sectors. And so I think that said, I'm really pleased to be here, Lou, and anxious to share a little bit more about it, what we'll call exascale computing. I've got a lot of material to share and really anxious to do it and appreciate the opportunity, Lou. Is it okay to share and
yes,
take off?
Please do.
Okay. Let's see here. Can you see that? When I say that, my slides, and if I do slide.
I see it.
Okay.
Full screen.
All right. So I'm going to go ahead and I'm going to move quickly, but anyone there, and certainly Lou and anybody here can speak up and interrupt or chat. We can hit it later. But again, Lou, I've got kind of roughly an hour or 45 minutes or so.
Yes, that'd be great.
Okay. All right. The exascale computing era is here. Reflections on then and now. And then is going to kind of be, where were we 6 or 7 years ago? Where are we now? So we're talking exascale applications, and then exa is 10, is 10 to the 18 zeros, okay? 1 and 10 to the 18 floating point operations per second. And we'll talk a little bit more about what that means. But, an exascale application are a particular set of applications we've been supporting in this project to be ready to go on day one. And basically, these are applications that are targeting national problems of interest, problems that are amenable to simulation, problems that are not solved today. And in particular, you see a list of bullets here for the kinds of outcomes we expect for these applications to, if not solved, to be kind of help solve. And you can see this spans all the Department of Energy space you can think of. A lot of people don't necessarily appreciate that there's a lot of discovery science, more fundamental science the Department of Energy, or DOE as I call it, supports, as well as, of course, national security, energy, energy production, transmission, fundamental science for energy, et cetera. And so you can see here, and I'll provide these slides as a leave behind. So a lot of my slides are fairly wordy. I'm thinking that they might be useful to reference back after the talk. So I'm going to move pretty quickly because I'm excited to cover kind of a lot of material. So if we think about the Department of Energy, there are 17 national labs across the complex, and 6 of the national labs have historically been involved in high performance computing, or HPC as we call it. And they're shown here in the bold dark: Oak Ridge, Argonne National Lab, Lawrence Berkeley National Lab, and then the 3 NNSA National Labs, Los Alamos, Sandia, and Livermore. And what's shown here is really over the past decade, these are kind of some of the major systems procured, deployed, and operated. And so we've been focusing on really exascale systems that are, like I said, going to be able to execute 10 to the 18th floating point operations per second or more. And a floating point operation here is, of course, an add, subtract, multiply, etc. And you see the Frontier system and the Aurora system and the Livermore system. Those first three systems we're targeting in this project. And the Exascale Computing Initiative, or ECI, in the Department of Energy is a broader initiative that encompasses the procurement and deployment of these three systems, plus the project itself, ECP, Exascale Computing Project, which is responsible for building the first mover applications in the software stack that's going to go on these systems. Just kind of looking at the Frontier system, which is here at Oak Ridge and supporting users as we speak. These were not simple projects that are executed over a few months or a few years. Really, these were more like decadal efforts. And you see this slide from Justin Witt, the project director for the Frontier system. We've been thinking about doing more than think about, but planning for Frontier installation for a number of years. And you can see some key touch points that's gone on really since well over the past decade. In 2007, when they first started talking about the science drivers. What are we going to do with this system? What are the drivers from the Department of Energy, and how can we be ready to really deliver consequential solutions for the nation on day one? The Frontier system, and you can find this online. Here are the specs and the speeds and feeds for the system, and some incredible specifications, and the ability of this system from a hardware point of view is something we never really dreamed about, even really a decade ago. The system has 2 exaflop peak. DP is double precision floating point operations per second, or flops. I put in blue kind of some of the things that are more interesting, at least to me. Has almost 10 petabytes of memory, so lots of memory translates into being able to have very complex physical phenomena that I'm modeling to be able to load it into memory and go after these equations. A given node is quite. It's basically the system has AMD hardware, an AMD CPU, and 4 AMD GPUs, and I'll show you a little bit more about that here in a moment. But the one node is almost 200 teraflops, which is incredible. If you think about the late 90s, the Department of Energy fielded its first teraflop system. And now here, 25 years later, one AMD GPU card is over 50 teraflops. That's how fast this whole community and this technology moves. So a Frontier node, again, as I mentioned, has an AMD EPYC CPU. It's known as a Trento, and 4 MI250 GPUs attached to it. What's really nice is it's coherent memory. So basically a terabyte of coherent memory on the node, and each GPU has a direct link out to other GPUs. It's called GPU Direct, of course, on Frontier. So Frontier consists of order 75 cabinets, and each cabinet has 128 nodes. So each cabinet has north of 25 petaflops of capability. So yeah, somebody's been around a long time. I continue to sort of be amazed about the speeds and feeds of this system. Again, you can go online and kind of see what's there, but one node being 200 teraflops is pretty incredible. And kind of 75 cabinets for the entire system. You need to be able to read and write data, ingest data quickly, and output data quickly. And that's not just for traditional mod sim, where we're solving a system of partial differential equations, but also for machine learning. We want to be able to ingest data very, very quickly to do training. In fact, I would argue Frontier is the smartest system in the world, being able to train, I think, multi-trillion parameter AI models. So you need to be able to ingest data fast, as shown here. One of the things that was really a gating factor for Frontier, for Exascale in general, about 10 years ago, and the Exascale Computing Project was able to invest with a lot of our HPC vendors to overcome, and that's power consumption. If we were to field a system made up of Jaguar components, and Jaguar was a system, as you can see, Oak Ridge has fielded Summit and Titan and Jaguar. We were able to actually deploy an Exascale system based on Jaguar parts. We could have done it, but it wouldn't have been useful, or most importantly, affordable. The power consumption per exaflop would have been north of 3 gigawatts. So that's just not feasible from many points of view. The target for an exascale system was to be below 20 megawatts per exaflop. And with Frontier, we actually hit 15. And so that required a lot of joint R&D investment with our HPC vendor partners here in the US. So that was a key concern that we addressed with our partners and been able to deliver on. Now I'm going to talk about the Exascale Computing Project, which is a part of the overall ECI. ECP mission is to build the apps, build the software stack, and jointly partner with vendors to make sure we could collectively fill the system that's used, useful, and affordable. And so the project itself has been executing now since 2016. It's a large project. I mentioned 6 labs are responsible for leading the project. I'm proud to say here at Oak Ridge, the project office, the key personnel responsible for managing the project, the project management aspect of the project sit here. The project itself includes over 1,000 researchers that draw heavily from the DOE national labs, but also heavily from industry and U.S. industry, from academia and U.S. industry. So a large project that actually is kind of in its last year of execution. And I'm happy to say that I believe we're going to cross the finish line and be able to wave the checkered flag of success. So ECP has really been able to kind of exploit and capitalize on these GPU-based systems. The first one being Titan. The project itself started in 2016, but a lot of the researchers had prior experience on the Titan system here at Oak Ridge. And what you can see is kind of a common theme of going from 1 GPU per node to, well, a 3-to-1 GPU to CPU ratio, now to 4-to-1 GPU to CPU ratio. And so, you can kind of look at the speeds and feeds with regard to the ability or the compute power on a per node basis, the power consumed overall. And so here at Oak Ridge, the leadership computing facilities supported by DOE have been following this accelerator roadmap. And here we call an accelerator. I'm sorry, we call a GPU an accelerator because basically these are pieces of hardware that are designed to accelerate certain floating point operations. In this case, a lot of matrix multiply operations really do scream, frankly, on this hardware. We've been able to show that we can exploit that for science. If your application isn't able to utilize the GPUs, you're really looking in the rearview mirror with regard to the compute capability. As an example, on Summit, it's a 200 petaflop system. Only about 6 petaflops reside on the CPU. And so you're really throwing away literally about 195 petaflops if you're not using the GPUs. So in a sense, you're really using an old system. So what we've done in ECP is to focus on, and similarly for Frontier, maybe a slightly higher fraction is available on the CPUs, but still only less than 10%. So your application really needs to be able to exploit the GPUs and really exploit the compute power and the concurrency you have in these GPUs, which is incredible. In other words, you might have the ability of kind of 1 billion separate threads. And so it's challenging to redesign your software and your algorithms to be able to exploit all that concurrency and be able to get at all the physics you'd like to get at. So what we did at the start of the Exascale Computing Project in 2016 is we worked closely with our DOE sponsors to define kind of 24 first mover applications, each of which targets a problem of strategic interest with the Department of Energy. There's one in particular that's very unique, and that's a co-partnership with the National Institute of Health, or NIH, on cancer research. And these applications, a lot of them were not really what I would call traditional HPC applications. They were not low-risk applications. They were, in many cases, high-risk applications. So the selection was based on the impact, the importance, and the impact of the problems they were addressing. And so basically, I'll leave behind, this is a very busy table, but it gives you an idea of the domains of the applications that we've been working with teams to develop. And basically, each one had a specific challenge problem. Each one had its own set of risks. The challenge problems, you can think of each application team was really on the hook to demonstrate that they could address the challenge problem as a kind of formal metric of success. And we're not necessarily claiming each challenge problem would be solved, but we want to be able to show that the physics and the science capabilities embodied in each simulation technology was good enough to to go after the problem in a new and consequential way. And so some of the applications had a performance metric to hit, and that's what the colored in green. In this case, at least 50x performance over the beginning of the Exascale computing project. And some all had capability metrics. Some had an additional performance metric, and that's the difference there in the color. So again, I'll leave behind these two tables because they're quite busy, but it shows just the breadth and the depth of the application portfolio that the project has supported. Now, in terms of being able to build an application that runs well or port an application that runs well on the GPUs, it's really a multi-step process. Porting code really does involve a certain amount of rewriting and profiling and optimizing, basically flattening loops and making some of your loops smaller, but it's really much more than that. You have to really look at the numerical algorithms you're using, and in many cases redesign the algorithms. You have the ability to, if your algorithm can be amenable to a reduced precision, in other words, instead of 64-bit, 32 or 16, that's even better. It's more expensive to communicate, so where you can avoid communications, et cetera, that's better. And adapt your models. Sort of gone are the days of store everything. Often you throw away and recompute. So you do a lot more on-the-fly computing. These are examples of the things to consider in being able to exploit the GPUs. What's also happened over the last decade, and this little diagram here, credit goes to Andrew Siegel at Argonne National Lab, who leads our overall application effort. We've really seen movement on the applications from just executing on a single CPU to now maybe a single GPU to multi-GPUs, now to diverse GPUs, because in the Exascale era here, we have Intel and AMD and NVIDIA all manufacturing and deploying very capable GPUs, to finally GPU resonant, meaning basically I want to build an application that says, okay, here I see some GPUs. I'm just going to go down there and live on the GPUs and do everything I can possibly do on the GPUs, because I get so much more memory bandwidth there and so much more compute capability. So we've really seen that happen over even the last few years. So this is kind of the new paradigm moving forward. So what you see here are, and again, apologies for the acronyms, but the application, some of the applications, what they've been able to do just in the last 3 or 4 years, and in this case, just on Summit, the system that's still, being in production here at Oak Ridge, you've seen tremendous speed gains. And this is on the left are science work rates for a given set of applications. And you see the horizontal line at 50, which is we wanted everybody to at least hit 50. And we thought, kind of in 2016, 50 was going to be very difficult. And for some applications, it is and will be. But for others, the performance gains by, thinking about new algorithms, refactoring, redesigning new algorithms has been tremendous. Many hundreds, or in this case, over 1,000 for some applications, which is a game changer for science. And so it's been something that we kind of never thought we would see, to be honest. ECP has not really mandated a particular programming model. And you might say, well, why not? Well, because it's not clear that there's one particular programming model. Basically, think of a programming model as a way to program the GPUs and to program parallel programming in general. And, there's not one model that really is one size fits all on a given application. And so what you see here is a nice plot of, depending on how productive the staff wants to be with regard to the application and how much control they want to have, you have multiple options here. And in this case, we've really worked with the teams and supported what we call motif-based frameworks, higher level abstractions, directive-based standards, and on down to very native or programming on the model. Programming on the metal. And so this is a nice diagram that shows that many applications have chosen different paths to be able to exploit the GPUs. And we have supported multiple paths. And we think that these paths are really going to be used and useful moving forward and sustained for applications depending on your priorities and your choices. So when we talk about a motif, just what is a motif? This is really coined by Phil Colella at Lawrence Berkeley many years ago. On the left are kind of the 7 more classical motifs, and on the right are 6 additional motifs that are associated with data science and machine learning and AI. And here a motif is really a common pattern of communication and computation. And what ECP did is we said, okay, applications themselves really use a surprisingly small number of motifs. So if we focus on being able to have certain motifs really scream on the hardware, we can have more impact and cross-cut multiple applications. So in ECP, we decided to go after what we call co-design centers that really focus on just a few motifs. And I'm showing here the 6 co-design centers and the 6 motifs that were really targeted because we felt like we had the best chance of being able to hit multiple applications. And I'll talk a little bit about a few of these motifs and really encourage folks to take a harder look at considering building your application based on some of these co-design centers that have been much more successful than I thought they would be, frankly, at the start. The first one is adaptive mesh refinement, patch-based mesh refinement. This is led out of Lawrence Berkeley. And this one, called AMREX or AMREX, at least within ECP, is already supporting 6 different applications, ranging from combustion to cosmology to astrophysics to multi-phase flow and accelerator design and wind energy. And what you see is a common pattern among a lot of our efforts, which is being able to sort of hide the complexity of programming on NVIDIA, which is using CUDA, AMD, which is using HIP, or Intel, which is using DPC++. And so basically the various programming models are supported underneath one sort of motif, in this case, AMRX. So the applications access AMRX, and all the complexity is frankly abstracted away by AMRX for them. And what we've also done in the past year is say, okay, what did things look like at the beginning of ECP and sort of the then, which was 2016, 7 or 8 years ago, and what do they look like now? And so these are very busy slides, but I wanted to leave behind the difference in the technology that's really happened as a result of ECP for in this case, AMRX, which has been quite remarkable, led by John Bell at Lawrence Berkeley. Let me give you an example of a combustion application that's built now on AMRX. And you see there in the bottom right, sort of a timeline of the evolution of 2 codes that did not exist at the beginning of ECP, Pele-C and Pele-LM, in this case, C for compressible and LM for low Mach number. And so you see the evolution of the capabilities, basically building in embedded boundaries, pushing particles, of course, bringing in AMR, being able to use particles for, following soot, following spray models, et cetera. And it's shown what the team has been able to do on Frontier very recently. And the thing to keep in mind with AMR, they're able to take a 60 billion cell calculation, which itself is quite remarkable. That translates to a couple trillion degrees of freedom, and be able to pull that off with less than micron cell resolution in key areas. And the effective this essentially is being able to take a kind of a 10 trillion cell requirement, and with AMR be able to make it a 60 billion cell reality because of the levels of refinement. Quite remarkable and quite impressive. And this is one example of one application that had a very specific challenge problem listed here, and they've been able to demonstrate that just on Frontier. Another one is ExaWind, which is led out of NREL, Mike Sprague. It is built on AMRX, and here you've now got an application that targets not just one wind turbine, but multiple wind turbines. Ideally, want to be able to simulate kind of a 40 to 50 wind turbine farm. Here, the challenge is to look at turbine to turbine buffeting. You've got turbulence behind one turbine that impacts impacts another turbine nearby. And studies have shown that this turbine to turbine buffeting, until we can understand it, is really responsible for a potential energy loss of maybe 20 to 30% of the entering wind into the farm relative to what maybe one could extract. So here we're looking at being able to extract more wind energy from turbine farms and being able to simulate multiple farms, and with local weather conditions and local ground topology all at once. So you're talking about a resolved turbine code application that's now integrating with a background wind application and a background weather application. Sort of a common theme here is multiple codes executing on the Exascale system, each interacting with one another during the simulation. Another co-design center that's very important or very consequential is our motif is looking at unstructured mesh motifs. We have a lot of applications that are built on unstructured mesh. And this particular co-design center, led out of Lawrence Livermore National Lab by Zanio Kolev as a PI, is not just focused on unstructured meshes, but let's do high order discretizations, high order finite element discretizations on the unstructured mesh. In this case, SEED is a center for exascale discretizations. And again, the common theme here is to be able to hide the complexity of implementing all these operations on GPUs away from the applications that essentially use this capability. So I encourage you to go check out if you're interested in high order finite element discretizations on unstructured meshes. This really, I think, is a great technology to build your application on. And you see there at the top here little images that reflect, again, order half dozen ECP applications that have chosen to build on this technology. And I think what I really like about this overall approach is the systems moving forward have lots of kind of free flops, as I would call it. So lots of powerful GPUs, okay, and not as much memory as you like, even though 10 petabytes is an extreme amount on Frontier. So now by executing your finite element discretizations with fourth, fifth, maybe even eighth order, I can get away with using less mesh, and so have a smaller memory footprint, and now be able to basically, get the same accuracy as a very highly resolved second order, but go to fourth or fifth order and use a lot less mesh. So I really like the approach here, and a lot of application codes have adopted it. In particular, here's an example of simulating a full core nuclear reactor, in this case with fully resolved LES CFD with the NEC-RS application, and use full continuous energy Monte Carlo neutronics. So this is an effort led out of Oak Ridge National Lab, where we're now going to be able to push maybe multi-trillions of particles for neutronics and be able to simulate an entire, in this case, small modular reactor core with CFD, not in this case subchannel, if you're familiar with the field. And they've shown that they can pull this off and be able to do this with a small modular reactor design. So here you see the then and now with neutronics, and the then and now with CFD. Again, with things like the SEED co-design effort, allowing the unstructured mesh capabilities to be able to be exploited with the NEC-RS code, which is a spectral finite element code, and be able to pull off fully coupled full core neutronics and CFD. I think it'll be a game changer to be able to really bring the capabilities here to bear on design of advanced reactors. Again, here's an example of the simulation that this ExaSMR effort pulled off. With you can see the number of histories 10 to the 12th per iteration, and the NEC-RS, which is the finite element code, being able to go after many hundreds of billions of degrees of freedom. So that's a nice problem. Again, I'll leave this behind, being able to show what their challenge problem was on Frontier. And again, I think this is going to be a game changer for advanced reactor design moving forward. And, I want to say too that we had basically these two applications. In this case, Shift was a continuous any Monte Carlo application out of Oak Ridge, and OpenMC, another similar capability out of Argonne, being able to couple together directly with the CFD capability. The NEC-RS application out of Argonne was quite remarkable. Now, another motif that's common in a lot of our applications is particles. Okay, I mentioned particles before with the Monte Carlo, but in this case, how do you make particles scream on GPUs? To push particles through the domain, to map particles to meshes, to mesh to particles. A lot of applications have this fundamental need. In this case, you see them above the cabana. Actually, if you have a Center for Particle Applications known as COPA, if you're a Barry Manilow fan, I guess your library is called Cabana. So in this case, the Cabana library is really a fundamental underpinning for a lot of different applications: molecular dynamics, particle and cell applications, material point methods, plasma applications. So another great example of being able to go after a fundamental motif, namely particles, and have it cross-cut and support many different applications. What you see underneath Cabana is, again, another common theme: abstraction layers, in this case, to be able to abstract away the complexity of mapping all these algorithms and software on the GPUs. And another really sort of common motif that's typical for a lot of applications is FFTs. And so one thing I didn't mention is, a given co-design center, motif co-design center, typically doesn't just have one motif. In this case, you've got solvers, FFTs, and particles all being kind of embodied within the Cabana library. So in this case, the Cabana library was this is kind of a then and now with how they started and where they are now. And it's been quite remarkable in that really the Cabana library wasn't even around at the beginning of ECP. And every application kind of had their own kind of purpose fit and one-off implementation of particles. So now we have a cross-cut implementation that's not one-off, that's reused and has an API that's appropriate for a number of applications. So, this COPA efforts led out of Los Alamos, and that's been another example for something very successful. So, how might the Cabana library be used? Well, one is an application that's going after additive manufacturing, first principle simulation of additive manufacturing, which is very, very important within the DOE complex. I don't think a lot of people appreciate how hard it is to print alloys that with high spec, high consequence specifications. And printed alloys are really still quite difficult and not a solved problem with 3D printing or additive manufacturing. And in this case, the exam effort, which is to be able to do first principle simulation of the additive manufacturing, leans heavily on particle-based methods. And here, the exam effort is really after trying to predict the as-printed microstructure of metal alloys. And by predicting the as-printed microstructure, one can be able to influence and influencing the process parameters of a given 3D printer, but probably more importantly, help design next generation 3D printers that do a better job in printing high spec metal alloys. In this case, it involves a lot of complicated physics, from laser e-beam deposition onto metal particles. So now you're talking about non-equilibrium melting, non-equilibrium solidification. You've got melt pool, and so you've got fluid flow with surface tension. You've got residual stress as a part solidifies. So thermomechanics and the exam effort has multiple codes that stimulate certain aspects of that process and are coupled together along the way. Probably one of our more complicated applications that the Exascale computing project is supporting. Another one is accelerator design. In this case, also uses particles. So now you're talking full particle and cell simulations, full 3D Maxwell solves, electromagnetics, and also really basically depends on adaptive mesh refinement. And this was our first application that got on Frontier delivered its challenge problems, hit its performance metrics, and also won the Gordon Bell Award last fall, which was a really a key kind of award in HPC space for applications that run at scale and solve new problems. And I really like this slide because the warp application at the start of ECP was mostly Fortran. You can kind of see how it stood in 2016, and now where it is in 2000 as of, well, actually 2023, not just 22. One of the things we've seen is a lot of our codes are sort of migrating from Fortran to C++. That doesn't mean that ECP now and moving forward won't support Fortran, but the choice was made here basically by the WarpX team led out of Lawrence Berkeley and Jean-Luc Vey. And you see the figure of merit over time. Figure of merit is basically the speed up of the science work rate, in this case, particles pushed per unit time. And so, the target was, let's get at least 50x, and you can see they've achieved an incredible kind of 500x in recent simulations on Frontier. So this code is going to be used for designing next generation accelerators. Accelerators used in medicine and used in industry and used in big science facilities like the LCLS at SLAC in the Department of Energy. And again, WarpX won the Gordon Bell Award, which is a very, very highly competitive award every fall. And we're very proud to say that ECP played a big role, and the Frontier system did as well. Another example application is known as the Exalt application, in this case, molecular dynamics, which are extremely useful for metal alloys and metals. And in the Department of Energy in particular, the LAMPS application coming out of Sandia. But really one of the kind of key gating factors for molecular dynamics is they're enslaved by these really, really small time steps, picosecond level time steps, when in fact you want to integrate out over milliseconds, microseconds, and seconds. So you can see here on the plot here that, by going to exascale, we can do larger domains. We can move to, hundreds of millions of atoms. But if we can't overcome that small time step, we still can't get out to more interesting time scales. So the idea with Exascale is to be able to push both limits, both size and time, but we need to also really design new algorithms to accelerate the molecular dynamic capability. So AMD, or Accelerated MD, Art Voter at Los Alamos really pioneered this, and we've been able to support further efforts by Danny Perez moving forward as the PI from Los Alamos. And what he and his team have been able to do is to be able to say, well, we can do replica dynamics. In this case, have many replicas of the molecular dynamics simulation on Frontier, in this case, or even Summit. And so what's shown here is an effort that ECP has supported to be able to execute many instances of LAMPS. And by executing replicas, and each replica integrates over a certain time step. And if you add together all those replicas, I can add together a bunch of sort of delta T's to a larger delta T, and be able to, with an accelerated molecular dynamics method, be able to integrate over much larger timescales, because the statistics will say that if once one replica overcomes a certain statistical barrier, I can stop the simulation. I can count all replicas together, add up those time steps, and be able to move forward with a much larger time step. So in this case, going after metal alloy problems in nuclear fuels and for fusion first walls, he's going after Danny's team going after extreme environments for metal alloys. And what's really cool also here is that he's been able to do quantum molecular forcing on the fly with the latte code showing there, and being able to go after a quantum level on the fly molecular forcing with the replica dynamics and get remarkable speed ups. This has also been a real poster child for using machine learning to be able to do on the fly, fits to DFT data as well as experimental data for the intermolecular atomic forces. So a good example of bringing in machine learning. And on that note, we're doing more than dabbling in machine learning and ECP. In this case, the Exalearn co-design effort is really not necessarily going after machine learning to replace a more traditional PDE-based simulation, but to really augment and accelerate the workflows of our applications. And you can see the four areas where this effort's looking to augment and accelerate the application workflows. In this case, designing surrogates, which is very important for sensitivity analysis and UQ analysis to basically impart or influence control. And that's being, in this case, using reinforcement learning. In this case, maybe control an actual experimental facility. Think of self-driving experiments. And design, it's really these machine learning physical structures, in this case, graph-based CNNs, to really sort of narrow down a set of molecular candidates, in this case for maybe a chemical catalyst, using machine learn-based design to sort of reduce the search space for some candidate molecules to be able to synthesize and test. And then inverse design, and an example shown here from the spallation neutron source, being able to look at scattering images and say, okay, I've seen that before. I know what that molecular structure might be. And so this has been an interesting effort where we've been able to kind of go after each of these four kind of pillars and be able to show that we can really accelerate and augment design. In the interest of time, I'll move quickly, but basically I'll leave behind some great examples in this case on surrogates, which I think have real potential for machine learning, be able to be trained on large simulations and be able to kind of understand what are the maybe dozen or so parameters that most influence the actual simulation, be able to use a lower dimension of surrogate to do more quicker sensitivity and UQ analysis. One of the things that's come up here is, with a system like Frontier, it could be actually train a model that's sort of multi-trillion or even 100 trillion parameters with a system like Frontier. We're all aware of ChatGPT and GPT-4 that was released in March. And one might say, hey, could we train a model maybe that large, but for science? In other words, training it on the literature in a particular area, the data in a particular area like material science or polymers. And one of the things we're looking at is I think that Frontier could actually be used, and we're certainly investigating that here at Frontier, here at Oak Ridge with Frontier, be used to train a new model based on really targeting science-based models, in this case for material science, alloys or polymers, to be able to really accelerate design and understanding. So that's something we're looking at as well. I kind of like this slide because there's a recent, not maybe 5 years ago, paper called Big, Beyond the Imitation Game. And the Imitation Game, of course, was the movie about Turing. And this paper talks about the importance of larger and larger parameter AI or machine learning models being really needed to get the accuracy. In this case, you're talking, this paper proposed a series of benchmarks for large language models. Of course, we would want to do benchmarks for science models, and shows the importance of a larger number of parameters. In this case, you can see the question asked the model, and a 2 million parameter model really didn't know what the heck it was talking about, and a 128 billion parameter nailed the question. The point is, as a community in science and HPC, we need to come up with similar benchmarks that really challenge machine learned trained model for science to get the precision and accuracy that we want. And so we have been thinking a lot about AI for science. In this case, in 2019, there was a report released from a lot of the DOE lab leaders shown here that really said, hey, what kind of comes after Exascale? It really might be concerted effort in AI for science. And similarly, there's a report coming out, in fact, this week, a more recent report on looking at basically how can we leverage DOE assets, exascale class computing, data infrastructure, large experimental facilities, the simulation capabilities that I've been talking about, and the interdisciplinary teams that we've been fortunate to support to really go after kind of certain areas where AI might be able to accelerate and augment our science workflows. The 6 themes are shown there, and I encourage you to kind of stay tuned. That report will be released, and we're certainly excited about the possibilities of a more of a deeper dive, a broad and deeper dive in this area to go after some of these key science things. Just a few slides to wrap up here. I want to talk now about some very non-traditional simulation capabilities that ECP has supported that are really, I think very, very important and on the mind, kind of the minds of a lot of us, and that's the power grid. And we've seen the recent, Texas incident, where we had an under frequency problem or a challenge, and, we had blackouts and brownouts. And so, we want to be able to simulate the entire grid. The U.S. grid consists of 3 interconnects. In this case, the Western, Eastern, and Texas interconnect. And if you look at being able to simulate just real time the grid in the U.S., it's much more than an exascale problem. If you wanted to simulate, the 1,000 or so grid energy generation points, the 10,000 distribution points, and on down to all the homes and all the smart devices. Now you're talking about billions of points that are well beyond an exascale capability. But in ECP, we've been supporting some new efforts to really look at, let's just look at maybe one interconnect, which is many hundreds of thousands of points. Can we actually simulate a couple scenarios? And one would be, we might lose 8 or 9 or a dozen energy generation points. What, due to, say, a severe weather event, what happens to the grid? Can we simulate the under frequency problem? Here it maybe go from 60 hertz to 59.7, and that's still problematic. By simulating that and understanding it, we can prepare ourselves for what we need to do real time to recover and maintain stability of the grid. And so that's kind of an under frequency problem we're looking at. Another one is just planning for the renewable energy sources on the grid now, whether it's wind or solar, that are more diurnal. And so how can we plan for the ebbs and flows of the renewable energy and make sure that we can plan to maintain the needs on the grid on a real-time basis. The operators need kind of minutes, seconds to minutes to make decisions. You can't have an exascale computer hooked to the, at least you can't now, hooked, right into where operators make decisions. But by doing these comprehensive exascale class simulations, we can develop, trustworthy data sets that we can train models for to use real time to inform the operators making these consequential decisions. So this is a very non-traditional simulation set where you're not using traditional PDEs, you're using discrete algebraic equations that are require mixed integer programming and new sort of nonlinear optimization techniques that are, really challenging and very non-traditional for our community that requires more research. Another non-traditional simulation is assembly. And so here you're talking about being able to, to do algorithms, to implement hash tables and implement very, very different algorithms on GPUs. In this case, in the Department of Energy, it's very important for the biological and environmental research, or the BER program. In this case, Kothe and her team have been able to basically take, production, DNA assemblers that basically assemble snippets of DNA into the overall DNA chain, and being able to re-implement assemblers that were capable of assembling kind of gigabyte or maybe terabyte data sets. And by being able to redesign those algorithms on systems like Frontier, they've been able to assemble 50 terabyte data sets, which has been, quite remarkable. And you're going to see this sort of technology become, the production assemblers at places like JGI at Berkeley. And you can see that this has a lot of implications with regard to microbiomes, where basically you can take samples of the earth where you have millions and communities of thousands or millions of microbial species, and be able to understand their DNA and being able to inform next generation vaccines and chemicals. Another very consequential application we're very proud of is that we've been heavily involved in climate modeling and Earth system modeling. In this case, the GPUs really afford a very unique opportunity to do subgrid cloud modeling. So you've got all these flops locally, and now you've got all this concurrency. So instead of having, or in addition to having more parameterized cloud models, cloud microphysics, cloud mixing models, now you can do a deeper dive in zones and cells that have clouds and do a deeper dive in terms of more fundamental mixing models. And it's known as basically an MMF cloud resolving capability. In this case, even with an Exascale system, a target for a climate simulation is kind of 5 simulated years per day. So even with an Exascale system, you're talking 20 days to do a century simulation. And so climate in particular and Earth system is a real driver for well beyond Exascale. But now being able to do these cloud resolve simulations are really important to reduce the uncertainties in these simulations, because clouds themselves, I think, are a major understanding and accurately simulating clouds are a major uncertainty driver in the Earth system simulation. In this case, ECP with Mark Taylor at Sandia being able to lead the effort, I think is targeting a key area of uncertainty, namely cloud microphysics. And finally, another application, and then I'll conclude with a few software technology products, is earthquake simulation. Of course, we saw the recent tragedies in Syria, and Venezuela. And I'm drawing a blank on where it was. I apologize. We saw the recent tragic earthquakes, and we want to be able to simulate what will happen. Certainly in this case, what's shown is a Bay Area, which is kind of a hotbed here in the United States. But being able to simulate what happens when an earthquake hits and to the waves propagating through the geologic strata, and how do they interact with the built infrastructure. In this case, it's shown that the smaller structures, 4 to 5 story structures, tend to couple more with the waves at the hertz, kind of frequency of 5 to 10 hertz. And with that Exascale, we can't be able to resolve those frequencies and also couple to these systems, these smaller 4 to 5 story systems. And Dave McCallum and his folks at Lawrence Berkeley have been able to show that by building a wave propagation code known as SW4, which the 4 stands for fourth order space of time, and then coupled together with these finite element structural codes, they've been able to show that they actually can resolve these frequencies, and with a system like Frontier, be able to really understand exactly what happens with earthquakes like this. And now, by understanding what happens, we can now retrofit more earthquake resilient structures and be able to plan in the future for being able to retrofit structures or design new structures that are much more earthquake resilient. So, and this has a number of ramifications for the Department of Energy, whether it's carbon sequestration or a safe deposit of nuclear waste. It's certainly the as-built safe infrastructure for earthquakes in general. Let me conclude by saying a few things about the software stack that lies underneath all these applications, because ECP is also supporting those applications. The software stack itself. Here is most of the community may be familiar with Scalapack, which is basically dense linear algebra libraries that a lot of our applications rely on. So we've been able to support the evolution of Scalapack, in this case, to Slate, which is a modern C++ library built on, built for GPUs. And so that's been a lot of these libraries are kind of underneath the covers of these applications. And in this case, this is a critical piece of technology and frankly developed a lot at the University of Tennessee, Knoxville down the street. I mentioned FFTs. FFTs are really ubiquitous across our applications, and Hefty, as it's known, also built by our University of Tennessee colleagues, really has moved to be able to be a game changer and really supports a lot of applications. So FFTs are very, very important moving forward. And on-node linear solvers, in this case, sparse linear solvers, sparse, in this case, even just sparse conjugate gradient solvers. So the Ginkgo solver in particular has been really, really more and more important moving forward for a lot of applications where they essentially execute batch solves where each GPU is solving its own smaller system. And a small system, even on the GPUs, is still millions of unknowns because of the size and the memory available for our GPUs. So a lot of all of our software products that we've developed and supported in ECP have been packaged together in something called E4S, the Exascale Scientific Software Stack. And we've been releasing this product at e4s.io for the last 4 years. Samir Shinde at the University of Oregon has been, on point for the release. And so I encourage folks to go to e4s.io. I think our last release was just a few months ago. It says November 22. I want to say it was March of 23. And there's literally over 100 full products there. Certainly a lot of the co-design center products I mentioned and the ones I just previously mentioned, but essentially every critical software product that our applications use is there, and it's out there for release and use. And I encourage the folks out here to give it a try. Let me just conclude by saying we have lots of lessons learned, and I think return on investment evidence to share. This effort has shown that the HPC community has really been never more vibrant than it has been right now. And basically, we're seeing a really important tipping point. That's namely this accelerated node computing with GPUs. They really are game changers. They're here to stay. And I encourage the community to really, don't sit on the sidelines anymore. I think with ECP, we've hopefully lowered the barrier to entry, de-risk a lot of these decisions to go ahead and go for it. Again, the Exascale era, 10 to the 18 floating point operations per second is here, and it's here for the future. And so, I think that we're really in the process now with Frontier demonstrating that this technology is a game changer, both the hardware and the software. And do encourage you to consider these key takeaways. Consider the software stack that's out there. Accelerated node is here to stay. All your laptops have GPUs, and so the software we built isn't really just boutique software that's only for exascale systems like Frontier and only for large problems. The software we built in large part has been developed on single nodes and even laptops. So it's certainly amenable and available for laptop on up to the largest systems in the world today. And but that said, I think I've worn out my welcome here, so I will stop, and happy to entertain if there's any time left, Lou, for any questions. I think I'll stop sharing if that's okay, Lou.
Yeah, stop sharing. So I think we have a chat if anybody wants to ask questions. I don't see any there right now, but let me just say, I don't know when you find time to sleep. This is an incredible body of work that you've been managing for some 18 years now at Oak Ridge, right? So tell me a little bit about the origin story for the high performance computing that we're into today, and how you got into it.
Sure. Well, let me first talk about how the project started. And I appreciate the comments, Lou, but I have lived this. It's been a career and a lifetime opportunity. It's been just unbelievably fun. And behind the scenes are probably a group of 30 leaders in the field that have been working with me. And so it's been a labor of love. But the project really started, like I said, it was kind of something we've been thinking about the last decade, because this sort of daunting change in technology, the step change in technology, namely GPUs and accelerators, were coming, and it looked like a train, frankly, and we weren't going to be ready for it. And so we realized we need to make this massive investment in software and algorithm work to be able to, execute kind of science on day one. And it's happening now on Frontier. With regard to me, my own personal story is I was doing my dissertation work at Los Alamos way back in the mid 80s. I got involved in, essentially developing an application to simulate the implosion of inertial confinement fusion targets. And I saw that I could address a key problem that I needed to address with computation, and realized at that point that I was hooked in building applications to target DOE science problems. And, that's really kept me, entertained and enthused ever since then.
Yeah, and now just recently they did the Q greater than 1 demonstration.
That's right. And, I've done more than dabbled in ICF. I was really happy to see that, and didn't think that'd happen because, back then I could see it was a daunting problem, and it has to do with maintaining the stability of that implosion to get it to get fusion. And certainly my friends and colleagues at Livermore, I was rooting for them, and it happened. So that's how it started for me. So
I mean, I could follow that line of thought for a long time, going all the way back to the implosion experiments that were done at Los Alamos back in the day.
Yeah.
And now you can simulate those. So what a world difference we have. One question I had for you was, when I look at your curve is about your power versus a capability, you seem to be asymptotically approaching a limit. So is the hardware coming to a point where you're going to have to do something different?
Yeah, and in fact, what needs to happen, Lou, is another injection of fundamental R&D, in my view, by the Department of Energy, but in all the government and commercial kind of approach. In talking with the vendors out there, they're still making not a fair amount, but a lot of progress in tackling the power, the power challenge. But at some point, we're going to reach some link scale limits on what we can do with CMOS, and it's known as Moore's law. Okay, and we're going to need to look at kind of totally new paradigms, analog computing, neuromorphic, and obviously quantum too. Quantum is not going to totally replace. It will augment and accelerate, certain workflows. But to field and I'll be retired, hopefully still alive by the time a Exascale computer comes along, and I think it's there. I think it's on the horizon. But to even think about something like that, you've got to tackle kind of 1,000-fold reduction in power requirements. And right now, there's not an obvious way to get there. And so, I think that said, back in kind of 2007 and 2009, I would have said the same thing about Exascale. And we did meet, Lou, with about 50 vendors late last summer. And when I say vendors, that's a term we use for, traditional HPC vendors, Intel, AMD, et cetera. But also there's a bunch of new vendors for AI hardware, a bunch of new vendors for quantum, and of course there's cloud vendors. And so the DOE leadership met with about 50 vendors, and what I saw there was pretty surprising and pretty encouraging in terms of the kind of the headway they're making. And they're not doing it just for DOE. I mean, as AI is a big driving market now, and that's really driving a lot of the focus in the commercial sector in sort of tackling some of these areas. So it really is going to require a public-private investment because the DOE mission needs are, not surprisingly, not the same in many cases as the private needs. So, I think it's going to require another strong push, like what happened with ECP, with this sort of co-investment to pull off that challenge. It's a daunting one, though, as you noted.
Okay, well, very good. It seems to me that the computational capability is out in front of a lot of the other application space at this point.
It is, Lou, and I think for the first time in my career, there were these two projects moving in parallel: the procurement and deployment of these first three Exascale systems, and a parallel software effort, because often the software effort lags, right? And code developers like myself, it's a labor of love, but it's nights and weekends. And this was a rare opportunity to really kind of have these two efforts in parallel. And, with Frontier now on the floor and the applications executing, we're actually to be able to see the fruits of our labor. But I didn't say this, and I did have it in the slides, but, we will have failed in ECP if we just have these boutique applications and software stack that only work on Frontier. I do think that these applications in the software stack will live for decades to come. And I think there'll be engineering and science tools for decades to come. And so this investment will see a tremendous return because a good application lives for many, many generations of compute systems. And I think we're going to see that with these applications. Time will tell. But a good application lives for decades, whereas these systems don't live but more than 5 or 6 years.
Yeah, it's amazing. The progress that you've made is incredible. I don't see any questions in the chat. Rami, do you see anything?
No, I don't see any either. In fact, gentlemen, I have to hop off here. So we'll just say that Doug was able to answer all the questions that people had throughout his presentation and call that a win. And I say we stop while we're ahead. How about that?
Okay. Well, Doug, thank you so much for taking the time. This is fascinating discussion.
Yes.
And I look forward to seeing you soon.
All right. Thanks all. Thanks, Lou.
Again,
Thank
for
you,
the
everyone.
invite. Really appreciated it. I enjoyed it. Thank you. Take care.
Bye.
Bye-bye.